webcam. Right? Ampere's law, right? Right, guys, okay. Right, Ampere's law, Ampere's circuit law and its applications. Let us try to recollect back what is Ampere's law, especially toroid. How to find magnetic field due to a toroid. Okay? I will try to recollect back few points related to other examples also, other applications. First, what is Ampere's law? Ampere's circuit law, or simply you can call it as Ampere's law. Ampere's law says that the closed line integral of magnetic field, or magnetic field, or a closed loop called Ampere'S loop. The magnetic field over a closed loop called Ampere'S loop is equal to mu naught times I enclosed. Mu naught times I enclosed is called Ampere's law. To understand this, so if we consider these mathematical name for Ampere's circuit law or Ampere's law. If we consider on a conductor, a simple conductor in which the current I is flowing into the plane, this is I1. Due to this, if we are asked to find magnetic field somewhere here at a point P which is at a distance R, even if one conductor may be there or two conductors may be there or different number of conductors may be there. So we have to construct a loop, closed loop. We have to construct a closed loop so that if current is going in at this point, if you say the magnetic field will be according to right hand thumb rule, you stretch the thumb in the direction of current, you stretch the fingers onto the point, direction of what? The palm gives the direction of magnetic field. Here this will be the direction of magnetic field over here. But if you consider a small element of length dl, then if you consider the closed loop, this closed loop, here you consider a small element of this loop. So magnetic field here, due to this conductor, or this this element, due to this small element, or you can say in the entire loop, if you are taking that loop in a particular direction called clockwise direction, it depends on the direction of the looping also you have to be careful about, especially directions of current. When you consider the what do you call enclosure current, if you curl the fingers in the direction of the loop, then the thumb direction will give you the direction of positive current. If you curl the fingers in the direction of the loop, the thumb will be into the plane. This gives the positive current. Okay? Whereas the current, outward current will be considered, or has to be considered as negative current if you are taking the direction of the loop in this way. Okay? So depending on the direction of the loop, the sign convention of currents you have to consider, that I already have given you. Okay? So here you can see that due to this, at this small element, magnetic field will be given as, according to Ampere's law, B dot dl. Here the B dot dl is equal to mu naught times I enclosed by this loop. If you want to throw out this, if you want the field, you have to consider small elements. Then the integral of BDL, if you add, the sum of all these BDLs gives you the total field that can be done by using the summation or integration. And addition can be done by using summation or integration. It is equal to mu naught times I enclosed. The I enclosed is nothing but just I. If it is one more conductor is there, if one more conductor is there, due to this current I is, let us say I2 is coming out, then you have to take that what enclosed current will be I1 minus I2. According to this loop direction, if you curl the fingers in the direction of loop, the current which is into the plane will be positive, the another one will be taken as negative. So I1 minus I2 I take. I enclosed should be I1 minus I2. This is briefly about Ampere'S law. Statement. Whereas by using this, how to find magnetic field due to straight current carrying wire? One is, another one due to, can consider cylindrical wire also, cylinder, due to cylinder. So let us see one by one, then toroid we will see. So if you have a straight wire, first one due to straight wire having current I, if you want to find the magnetic field somewhere here at a point P, which is at a distance R, you have to consider a closed loop. It is a two-dimensional loop. It is analogous to Gauss law in electrostatics. To find electric field due to a continuous charge distribution, we use Gauss law. There we consider a closed surface called a Gaussian surface. It is a three-dimensional surface. But here it is, Ampere'S loop is a two-dimensional loop. So if you construct a loop, a two-dimensional loop, and I will draw this properly. And if you consider this is the conductor is going up, and if you are taking the direction of the loop in anti-clockwise direction or clockwise direction, and fix that. If you are taking the direction of the loop in anti-clockwise direction, if you curl the fingers in the direction of, so this is the loop. Try to imagine this is the loop. If you curl the fingers in the direction of the loop, then the thumb direction will give you positive current. If the current I is going up, that we have to take it as positive. So according to this particular Ampere'S law, if you consider a small element of the DL, here again, imagine this is a loop, a current carrying conductor. Due to this, if you stretch the thumb and stretch the fingers on this point, the magnetic field will be along the tangent. Here the magnetic field will be along the tangent. So both of these are parallel to one another. So you can take integral of B vector dot dl vector is equal to mu naught I enclosed. Is nothing but I only in this case. So the first application of Ampere'S law, you see magnetic field B due to straight current carrying wire. Usually if you consider it as infinite wire, you have calculated the magnetic field with infinite wire by using Biot-Savart law. We have derived an expression for a finite wire, then you have applied for infinite wire and semi-infinite wire. In different cases we have discussed. So this is an infinite wire. If you consider, you can compare the magnetic field which we are getting here with the Biot-Savart law application also. Now, in this case, B, dl, cos theta, both are parallel. So theta will be 0, cos 0 is 1. Directly you can take BD integral of BDL. B can take this out, and integral of dl is equal to mu naught I. Where so this dl is going from dl throughout the loop we are taking. So sum of all dls will give you what? The total circumference. If this is the radius of this circle, loop is r, the integral of dl will be L. It goes from 0 to 2 pi r. If radius is r, you can take B into integral of dl is L with the limits 0 to 2 pi r is equal to mu naught I. This further can be taken as B into 2 pi r is equal to mu naught I. Therefore, you can take B is equal to what? B is equal to mu naught I by 2 pi r is the magnetic field due to this conductor. Now, if you compare this with the Biot-Savart law, you get the same. In Biot-Savart law, general expression is what? B is equal to mu naught I by 4 pi d into sin alpha plus sin beta. From Biot-Savart law, for infinite conductor alpha and beta are 90. So sin 90 plus sin 90 is 1 plus 1 is 2. So 2 into 2 gets cancelled, you get mu naught I by 2 pi d. But d you are taking it as r, 2 pi r. The same thing you are getting here. But here you will get the simplest one. The same thing you have got with a huge derivation. with a lengthy derivation in case of Biot-Savart. But again, within a few steps we will get it. So the G is little simplified one. There is little simplified one. Okay? Right. This is one of the application of Ampere's law. Another one, let us consider a cylindrical wire. A cylindrical wire. Can I erase this? Right. Right. See here, you can understand that in case of a cylindrical wire or thick wire in which current is distributed uniformly, I will give you just here that the derivation part we are not going to deal. It's very clear to give you. If it is a cylindrical wire having this is the axis, which thick wire or cylindrical conductor also can consider having this thickness is some r, and at a point P, if I ask you to find the magnetic field, okay, and if it is this cylindrical conductor, let us consider it is a hollow cylinder, cylinder inside it is hollow, nothing is there. So current is distributed only on outer surface. Let us say this charge is a cylinder, inside nothing is there. So current is distributed only, current is flowing only on outer surfaces. Following this, in that case, what is magnetic field at an inside point and an outside point? Right. To understand this, first let us consider a current is flowing in outer surfaces. Current I is flowing in outer surfaces. So let us, for our understanding purpose, let us just maximize this. Then you can consider this is the current I. At an inside point P, if you want to find the magnetic field, which is at a distance r, you have to construct an Ampere'S loop. You have to construct an Ampere'S loop with this radius as r. You have to construct an Ampere'S loop. So as from the Ampere's law, closed integral of B dot dl is equal to mu naught I enclosed. The current enclosed by this loop, as the entire current is flowing through outer surface, what is the current enclosed by this loop? Any current is flowing through this loop? No current is there. Entire current is outside only. So this enclosed current is 0. So you can write it as BDL is integral of BDL, you can take it as B into, of course, total circumference of that, it is equal to 0, and hence directly you can take B is equal to 0 at an inside point, inside, simply by using Ampere's law. You can understand directly that it is 0. Whereas in case of outside point, let us say this actually can find out the same thing by using Biot-Savart law also. Actually, Biot-Savart law can apply even to find the magnetic field due to a thick conductor or solid conductor. Okay, let us see that also if it is required. If we consider an outside point, this is an outside point Q, which is at a distance of course small r or r dash from this. Here again, to find the magnetic field here, to point at a point Q, you have to construct a Gaussian surface, symmetric Gaussian surface, like this. Now, just imagine that this is a conductor, I have constructed a Gaussian surface. Now, at this point Q, closed integral of b dot dl is equal to what? Mu naught into I enclosed. Mu naught into I enclosed. So here BDL, for this current is moving up, B is along the tangent, DL also will be along the tangent. If we take, what is this? Anticlockwise loop, then B into 2 pi r, B into 2 pi r is equal to mu into I. So simply we will get mu B is equal to mu naught I by 2 pi r at outside point. Then outside point. Is it clear? So this is similar to this thin straight conductor, even though it is a cylindrical wire, but hollow cylindrical wire. Yes, this is another case. Another case. But to find magnetic field with thick cylindrical conductor, you have to use a different one of the parameter called distribution, like charge distribution, where current distribution have to take. Charge per unit length, charge per unit area, charge per unit volume. You have used right? Current, what is that? Linear density, surface density, and volume density. Those parameters you have to use. According to that, you can observe that in case of a solid conductor, magnetic field inside will be directly proportional to the distance, whereas outside it should be inversely proportional. Inversely proportional to R. So from that you can understand that in case of a solid cylindrical wire, solid cylinder, you can say B is proportional to I, or you can say proportional to R. Of course, I is distributed uniformly, so B is proportional to R inside and B is proportional to 1 by R outside. So that we have to observe for cylindrical parts. That this we are not dealing now. This for understanding purpose. This for an idea I am giving you this. Now actually our point is to discuss how to find magnetic field due to a toroid. Now let us get into the actual concept of toroid part. In case of solid, it is in case of solid conductor. In case of this, it is directly proportional, of course. So it is inversely proportional here, outside case. Inside it is 0. But in case of solid cylinder, inside it is directly proportional to R, but outside is inversely proportional to R. Here inside is 0. So if you draw a graph, for B versus R for a hollow cylindrical wire, inside from R equal to 0 to small r, you can take capital R also. You can take this as capital R. Radius is capital R. For this radius it is capital R. Then till surface it is 0. If it is capital R is radius, till this it is 0. Then from here onwards it decreases. Right? Whereas in case of solid cylinder, this is B and this is R. Then R from center to R is equal to capital R will be linearly proportional. Then it will decreases gradually as it is inversely proportional to outside. That is for the solid cylindrical wire. That is for hollow cylindrical wire. Right. Now let us try to understand how to apply what is this Ampere'S law to a toroid. First of all, what is a toroid? As directly I am presuming and by thinking that you remember the concept of solenoid, let us get into the concept of toroid. So, toroid is nothing but closed solenoid, you can call it as. Or endless solenoid is called toroid. Endless solenoid is called toroid. So you know solenoid is nothing but this kind of helical current carrying wire is called solenoid. Yes, if you bend this and if you attach both the ends, then it looks like this. So if this is kind of this kind of endless solenoid will be called as toroid. This wire you can wound on some core. You can wound on a core. Then, so let us try to understand this shape representation of toroid with the help of a core. There is a core, right? On this we are winding the wire. So we are winding the wire. Okay. This you have to imagine that internal inside part will go like this. You can consider this either way. Okay, and you can consider the current is entering here and leaving here, or entering here, leaving here. Either way you can take it. This is called toroid. So you can consider this way or this way, either way. This as per your convenience. In this, when current I is flowing, current I is flowing, let us consider current I is flowing here and is coming out. It is getting in and it is coming out. When it is flowing like this, it goes in, it comes out, in and out, in and out, in and out, and for every turn. In this entire this shape is called what? Toroid. So simply we say endless solenoid is called toroid. Note down. Endless solenoid is called toroid. Right. To find the magnetic field due to this, by using Ampere'S law, how you have to proceed? Let us try to consider here 3 points. First, what will be, if you say this center is O, something like that, somewhere here at a point P is a point inside the toroid, but it is outside this core part. Another point Q, it is inside this core. And another point R, it is completely outside the toroid. So, to find the magnetic field at these different points, how you have to proceed? What are you doing? How we have to proceed? Let us see. Right. We have to first consider the distance of this point as, for every point you can take small r provided here. Let us consider this thickness will be very, very small. For ideal one, comparing this distance, you can take R1, R2, R3, R. In every case, you can take this distance will be R. So this is R. To find the magnetic field here at this point, at a distance R from the center, you have to construct a symmetrical loop, circular loop. This loop, and of course here this will be going like this. This will be this loop like this. So here there will be no current enclosing by this loop. There will be no current enclosing by this loop. So simply, I can say at P, first thing, closed integral of B dot dl vector is equal to mu naught into I enclosed. Here I enclosed is 0. So inside the toroid, which is not inside the axis part of this core, is 0, because I enclosed is 0. Because I enclosed is equal to 0, you can say B at P is equal to 0. B at P is equal to 0. Whereas the second point is at Q. At Q, this is the point Q. To find this, if you construct a loop, closed loop, before discussing about this Q point, let us first see at R. At R, this is R. Let us say at a distance. This is the distance R. Construct a gauge, what is called Ampere'S loop for this. This is also circular loop. And if you observe here, the amount of current in this, whatever current comes out, enters, comes out and enters, comes out and enters. How much current comes out at this point? The same amount of current goes in. So we have to treat this as in the cross-sectional view. If you see, if you say like this, the current I is coming out, I, and same amount of current is going in, which is surrounded by the loop. So the total enclosed current is I minus I. This is plus I, this is minus I. So I minus I will be 0. So enclosed current for the point R should be, enclosed current should be equal to 0. So therefore, you can say integral of B dot dl is equal to mu naught I enclosed, which is equal to 0. So you can also say B at R is also equal to 0. Then outside point is also 0. Now you can see the third point, that is at Q. The third point, which is on the axis, which is called as perennial axis of this, or inside that core, axis of the core. Inside the axis of the core of the toroid, magnetic field is given by. To find the magnetic field here we have to construct the Ampere'S loop. So here, if we consider this point as current is coming out and going in, so current I is coming out here and the same amount of current I is going in. So if you consider that symmetrical relation between this I and I, out current and in current, because this is the loop that outside current you shouldn't consider, only inside current only you have to consider. So in this, as an outside current you shouldn't consider, only inside current only you have to consider, that current which is going in only. So current I which is going in only you have to consider. Then you can say integral of B dot dl, integral of B dot dl is equal to mu naught I due to one turn. If total n number of turns are there, total capital N number of turns are there, a number of turns per unit length is, you can take it as a small n. Then, or you can say for n number of turns, capital N number of turns, the total current can be taken as I into n. I into n. So here integral of B dot dl, you can take this as B into dl is 2 pi r, or total length, circumference. You can take L r 2 pi r. If you take this radius is r, then you can mention this as B into 2 pi r is equal to mu naught I into n. So this 2 pi r, if you bring it here, you can write it as B is equal to mu naught I into n by 2 pi r. Completely you can write 2 pi small r or whatever it is, this will be the magnetic field here. But this 2 pi r is circumference, you can take total length. Total number of turns by total length can be taken as number of turns per unit small n. So this can also be taken as is equal to mu naught n where small n is total number of turns per circumference of this toroid, is nothing but total length of the toroid. So this way I can express the magnetic field. So you observe at different points, only magnetic field will be present at the inside point of this toroid. You can say axial point of the toroid, or you can call it perennial axis of the toroid, provided its thickness is very very small comparing with the radius part. We will not consider inner radius and outer radius, only single radius we consider. So these are few points you have to remember about the toroid. Okay, solenoid part we try to revise once, go through. In solenoid also we have observed that magnetic field on the axis is derived an expression right for a solenoid. What is that? Mu naught Ni by 2 into cos theta 2 minus cos theta 1, or cos theta 1 minus cos theta 2, depending on the angles. There again is some special cases we have discussed. Exactly, if it is the infinite solenoid and an ideal solenoid, mu naught Ni will get. Right? An infinite solenoid. At end of infinite solenoid, either ends, it is mu naught Ni by 2. So try to go through those and compare with this, then you can understand how to find the magnetic field due to toroid and also due to solenoid part. Right? This is the briefly the concept of what you call it, Ampere'S law applications. This application I thought is recovered backwards. Go through this and understand the simple points and try to work out some questions based on this. So I am winding this.